Sorry for the technical incident at the end of the previous video. So to continue from where we stopped, the plastic deformation we said according to Tresca, we need to calculate the principal stresses sigma 1, 1, sigma 2, 2, and sigma 3, 3, or sigma 1, sigma 2, and sigma 3. So these are the same depending on what this is just a symbol. So we just calculate, after we calculate the principal stresses, just we find the difference between any two of them. And if any difference is greater than the yield strength, which is the property of the material, we will have plastic deformation. So to clarify, let's take this example here. Given the following state of stress at a point P in a solid object, so this is the state of stress. The yield strength of the material is sigma y 350 megapascal. We know that the yield strength is 350 megapascal. So we have the status at the point P. Will the material undergo plastic deformation at the point P according to Tresca criterion? So the state of that, how do we do it? How do we develop it? So we start from the state of that. The first step, always as we said, is to calculate the three principal stresses: sigma 1, sigma 2, and sigma 3. Here we can see that sigma 2 is already, we don't have any shear in this in the y direction, so we can directly find that 500 is a principal stress. But anyway, if we find the eigenvalues, we can find these three values for the principal stresses. So after we find the principal stresses, here's the three principal stresses. So now that's the first step. The second step is so sigma 1 minus sigma 2, 500 minus 400 is equal to 100, is less than sigma y. So sigma y is given 350. So 500 minus 400, this is the first difference. The second difference, 500 minus 200, sigma 1 minus sigma 3. So it's also less than sigma y, and sigma 2 minus sigma 3, 400 minus 200. So we compare the three cases. If any of these three was greater than sigma y, you will have plastic deformation. Now, because all the three here were less than sigma y, so we will not have a plastic deformation. That's Tresca criterion. So we find the principal stresses and we do this difference. So we can see that at the point P, we will not have any plastic deformation according to Tresca. That's it. Very simple. Now the second criterion was proposed by von Mises. So von Mises just the von Mises criterion is based on the strain energy, but not any strain energy. It's based on what we call the distortion strain energy, or the strain energy which is responsible for the change of shape. So what von Mises suggested is to compare the strain energy responsible for the change of shape at the point that we are studying, or what we call the distortion strain energy at the point, comparing it to the same energy which corresponds to the yield strength in the tensile test. Now to summarize, the final result will be like this. After we find the principal stresses, we find this, what we call this equivalent stress, so sigma 1 minus sigma 2 squared plus sigma 1 minus sigma 3 squared plus sigma 3 minus sigma 2 squared over 2 the square root, we compare it to sigma y. That's to summarize very quick. That's what we need to understand. So after we find the principal stresses, we find this value, we compare it to the yield strength. This value here is greater than sigma y, so we will not have, this means that we will have a plastic deformation. If it was less than sigma y, we will not have then a plastic deformation. So just to understand what do you mean by distortion strain energy, so we know the total strain energy, as we said in the stress strain curve, is the area below the curve. But here in the case of three stresses, like that's the case that we have here in 3D case. So it's the sum of 1/2 stresses times strains. So hydrostatic strain energy and distortion strain energy, what are these two? So with the total strain energy, there's already the one that we already defined. We can see that it contains two parts. One part was responsible of the change of volume or the change of size, called hydrostatic strain, so we don't have any change of shape. And one is responsible of the change of shape, so the distortion. When we say distortion, means change of shape. So the total strain energy that we defined is equal to comprises two components, one responsible for the change of size and one responsible for the change of shape. And according to von Mises, this one is the one responsible for yielding. So this one will not affect yielding, as we saw before. So how do we calculate this one? So 1/2 the sum of sigma 1 epsilon 1 plus sigma 2 epsilon 2 plus sigma 3 epsilon 3. And we know that epsilon, if we have the stress, we can find the strain as we said before. So using the Young's model specificity and the Poisson ratio. So if we just replace epsilon 1 by its value, by its value, and epsilon 2 and epsilon 3 with rearranging the terms, we can this is the total energy, the total strain energy at the point P when we are using the three principal stresses. So it's using the stress tensor. So this is the total strain energy contained at the point P. Now how to find the hydrostatic strain energy? So using the sigma average. Sigma average we already defined it when we defined the bulk modulus in lecture 4. So you can go back and check it there. So this stress is responsible for the change of shape. We can find the relation between this and between the dilatation. What we call dilatation. So the details already found them in lecture 4. So the idea is that if we replace here all the stresses by sigma average and the arrange the terms, we can find this part here is the part of energy which is responsible for the strain, for the change of size or the change of volume. So this is the total energy contained at the point. This is the energy only responsible for the change of size. So to find the energy contained responsible for the change of shape, we just subtract this term from the total energy. So subtracting this term from this term, we can find the distortion strain energy. So that's the value of the distortion strain energy. So what you need to understand from all this slide is that if I have a point P, I will have a total energy at this point, strain energy, based on the stress tensor that I will have there. I will have a part of this energy will be responsible for the change of size, or the change of volume will be equal to this, and a part responsible for the change of shape, what we call distortion strain energy, equal to this part. Now this is for the point peak, or if I have the principal stresses. So von Mises suggested that this is the same one here. Von Mises suggested that if this distortion strain energy at the point P corresponding to this three principal stresses is greater than the yield distortion strain energy. So the distortion strain energy when we have only yield strength. So this is if I have only yield strength, this will be the distortion strain energy if I have only yield strength. So if this term is greater than this term according to von Mises, then only on this condition we will have plastic deformation. So the distortion strain energy at the point here in red is greater than the distortion strain energy corresponding to yield. Doing the development, we find the relation that we already defined. So how to use the von Mises? That's what we need to use. The first step, we calculate the three principal stresses. If I don't have the principal stresses, then we calculate this term, this square root here, and we compare it to sigma y. If it's greater than sigma y, we will have a plastic deformation. That's it. That's how we use the von Mises criterion. So that's the summary here. So that's the example, the same sentences that we already did with Tresca. Let's now do the same. So we have sigma y is equal to 350 megapascal. That's a property of the material, the yield strength of the material. We have the stress tensor at the point P is given, and we need to check using the von Mises now, will the material undergo plastic deformation or not. So always the first step, always if I don't have the principal stress, we need to calculate the principal stresses. So always without starting any analysis directly, we calculate the principal stresses, or sigma 1, sigma 2, and sigma 3. Then we calculate square root of sigma 1 minus sigma 2 square plus sigma 1 minus sigma 3 square plus sigma 2 minus sigma 3 square over 2. So because we have square here, we don't care about the order sigma 2 minus sigma 3 or sigma 3 minus sigma 2 is the same here. And we find 265 megapascal. Now we know that the yield strength is 350, so the yield strength, the equivalent stress here is less than the yield strength, and so according to the von Mises criterion, we will not have any plastic deformation. So that's it. So also very simple. Just always once we find the principal stress, just calculate this term and compare to the yield strength, and that's it. So now we define two different criteria, Tresca and von Mises criteria. Now this is what we need to understand, that these two criteria, both of them are used in engineering. So when we are designing a component, we need to check if it will yield or not at a point, at a critical point. We have this rate of stress at this point, we find the principal stress, and we use the two criteria to check. But normally, and we just need to pick one among the two, so we don't use the two at the same time because they will give a little bit different result, but the results are close to each other. Now this graph here, and this principal stresses, if we just draw the principal stresses, the circle here represents the part on that represents the restriction of of the von Mises. So if any point, any principal stress is contained in this circle here, according to von Mises, we will have we will not have a plastic deformation. According to Tresca, only the points inside the dashed line will not lead to plastic deformation. So if I have principal stresses, let's say sigma 1 and sigma 2 at this point here, so according to von Mises, we will not have any plastic deformation, but according to Tresca will have plastic deformation, which means that Tresca we need to understand that Tresca is more restrictive or more conservative criterion. What does it mean more restrictive? That in some cases von Mises, if we use von Mises, we can find that we will not have plastic deformation. But if we use the Tresca for the same state of stress, we will see that we will have plastic deformation, which means that Tresca is more, as we said, is more restrictive. So it will give us more constraints in order to check. So how we can choose von Mises or Tresca when we choose one or the other, depending on the engineering applications that we have. So von Mises will give us less restrictions, but at the same time, maybe if we use Tresca, it will be safer for us. But maybe we will be using some restrictions that are unnecessary. So maybe we'll use more material. Let's say it will lead to more cost. So we don't. So depending on the applications that we have and the degree of safety that we need, we can pick one of the two criteria. Now to understand all of this here, to understand all of this idea, and also to do a revision of what we just said about the criteria and what we need to understand from the chapter. Let's take this example here. This example also we can revise a little bit what we had in the previous lecture about the thin shell vessels. So let's read a cylinder of steel of 10-meter diameter. So we have a 10-meter diameter cylinder of steel, closed ends. It's containing a gas, a propane, at the pressure of 25 atmosphere. So inside we have a 25 atmosphere inside the cylinder. So estimate the minimum thickness required if the cylinder cannot deform plastically. So that's the maximum that's the yield strength. So that's the property of the material of the cylinder that's given. So we need to use Tresca and von Mises criteria in order to check the minimum thickness that we need to when we do the design of the cylinder. What thickness should be, how thick should be the cylinder be in order to prevent it from deforming plastically. So we don't want it to prevent plastically. We use Tresca and von Mises. So how do we deal with this problem? The first part, we need to find the stress state in the wall of the cylinder. That's the first point to do. How do we find the state of stress? So we know the radius, the diameter is 10 meters, so the radius is 5 meters. The pressure inside is 25 atmosphere, so let's convert it to megapascal. So let's keep just, if we go back, to keep all the units in megapascal. So when we compare later, we don't have any problem. So 20.5 megapascal. So here the radius is 5 meters. It's safe to assume that the thickness is very small compared to 5 meters even if we don't have the thickness. So let's assume that we have a thin cylinder here. A thin cylinder, so sigma r is equal to 0. The radial stress is equal to 0, while the tangential stress and the axial stress are not equal to 0. These are the formulas that we can use for a thin cylinder. So this is a revision of what we did last time. Here because it's closed end, so this one, if it was open end, this sigma m or sigma x that we call the same will be equal to 0. So here we have the three stresses. Also, so if we want to build the state of stress, we will have it like this. We said we don't have any shear in the case of a cylinder, a thin cylinder. So these are the three principal stresses. Here the idea is that in the case of a thin cylinder, we already have the principal stresses. If we did not have a thin cylinder like this one, if you have any other state of stress, the first step, as we said, is to calculate these three principal stresses. But here in this case, we already have them as a principal stresses. Now, as you can see here, the principal stresses depend on the thickness T. So our objective is to find the thickness T that will allow us to prevent plastic deformation, according to Tresca and according to von Mises. So according to Tresca, the first part of the problem, we know that according to Tresca, we need to find the principal stresses that were already found. Then we need to compare this three differences, sigma 1 minus sigma 2 with sigma y, then sigma 1 minus sigma 3, then sigma 3 minus sigma 2. And this we should do it if only one of these three is greater than sigma y, we'll have plastic deformation. But here, so we need for the three of them should be less than sigma y in order to prevent plastic deformation. So let's take the first one, sigma 1 minus sigma 2, so 12.5 over t minus 6.25 over t less than 250. If we do the development, we find that the thickness should be greater than 2.5 centimeters. Now we do the same with sigma 1 and sigma 3, so 20.5 over t minus 0, because this is sigma 1, this is sigma 2, and this is sigma 3, 0. That's what we found in the previous slide. So also the thickness, so we can find the thickness is greater than 5 centimeters here. And also if we do sigma 2 minus sigma 3, so sigma 2 minus sigma 3, or sigma 3 minus sigma 2, because we are using the absolute value, should be less than 250. So this one should be positive always, because the 250 is a property of the material, it's always positive. So always we compare a positive value to sigma y. So the important that also we found that the thickness should be 2.5 centimeters. So in order to choose the most restrictive condition, in order to respect all the three equations, we need to find a t greater than 5, because it automatically will be greater than 2.5. So according to Tresca, the thickness should be greater than 5 centimeters. Now if you go back to the problem, it's written use a safety factor of 5.5. What does this mean? So after we found everything now, so the thickness we found should be greater than 5 according to Tresca. With a safety factor of 1.5, we multiply the value here by 1.5, so 7.5 centimeter. So now when I want to go to do the design, to design the cylinder, I will say that I need a thickness at least of 7.5 centimeter in order to prevent the plastic deformation with a safety. So I had some range of safety here of 1.5. So the theoretical value is 5 centimeter. With some safety, I will use 7.5 centimeters. Now this is according to Tresca. So according to, so here this is the minimum thickness. Okay, so this is minimum thickness, not maximum thickness. So the minimum thickness should be 7.5 in order to have some safety and to prevent plastic deformation. Now for according to Van Mies, it's also similar. Always we need to calculate sigma 1, sigma 2, sigma 3 that we already have, but here we don't need to do three different equations. We just find this equivalent stress and you compare it to sigma y. So sigma 1 minus sigma 2, so 12.5 over t minus 6.25 over t, that's sigma 1 minus sigma 2. So I take t here to the outside t square, so we can do the development. And if we solve this equation, we find 10.82 over t. According to Von Mises, this term should be less than sigma y in order to prevent the plastic deformation. So if I compare this term to sigma y, so we find that the thickness should be greater than 4.3 centimeters. If we use a safety factor of 1.5, we just multiply this value by 1.5, which means theoretically using Van Mises, if I want to design this cylinder, I need to use 4.3 centimeter thickness at least, or 6.45 centimeter if I want to have some safety. So the minimum also this minimum thickness should be 6.45 centimeter in order to design the cylinder according to Von Mises. So now just if you compare here the thickness, so according to Von Mises, the minimum thickness should be 6.45, while according to Tresca it should be at least 7.5. So you can see that Tresca is more protective, is more safe, is more restrictive. That's what we said. But as we said, but if you go and design your cylinder based on 6.45 centimeters, it's also okay according to what you have as resources. Because if you use 7.5 centimeters for a very large cylinder, it will also be a cost. So we can see also that Tresca maybe will give us more restriction, but also more cost. So that's how we can. So we choose according to the application and to the degree of safety that we want. Now everything that we learned in this lecture about the first chapter about the plane stress circle of Moore and about the yielding criteria, we'll do them we'll do some problems on them together in the tutorial tutorial number 6. So we can do a revision, also we can compare, we can do draw a tri-circle of Moore, check how we can use it, but just for us for now. We do a revision of Tresca and von Mises because these are the criteria that are used in engineering, and we also use the same equations here. As you can see, it's very simple. Just calculate the principal stresses and just directly find and compare to sigma y. Sigma y, I repeat, is a property of the material. The y here mean yield strength. So this is a property of the material. So that's it, and then we discuss and during also the session and then during the tutorials. Thank you.